Hello, my name is Kelly Kramer. This is the final assignment where it is my turn to teach everyone else what I've learned so far in this semester. So let's get started. So the first slide we come to is 3D building history. Now, the most significant starting point in this would be starting with Charles Hull. He filed a patent in 1986 for a 3D printing system that used a reservoir of polymer and then a laser shot into it to solidify it. This was called the SLA-1. It was considered the very first 3D printer that was made available. It ran between $3,200 and $4,600, and it kind of was the mother of 3D printers. Things were starting out pretty slow in the beginning, especially around 1971, as the beginning of the actual software that was going to be used to control 3D printers was still largely in its infancy. There were no software that was designed specifically for a personal computer, so they were far more technical based. The very first one was a simple 2D um, pen and display drawing. You would draw sketches using it. And that progressed and led on until Patrick Hanratty in 1971. He created the first fully user interface based CAD program that he programmed in Fortran. This kind of opened up 3D printing to a much larger market. You no longer had to have extensive computer knowledge to program and use these pieces of equipment. Later, Autodesk became the first to release a 2D piece CAD program in 1982 that was available for PC. This fully removed the limitations on the software for 3D printers that had been originally a serious issue. Just because the required technical expertise was so high, being able to reduce it and make it user interface based and putting it on PC really opened the doors for expanding the industry greatly. So next we actually go into different types of 3D building software. Now there's all kinds of software available, and the list on the screen are just some of the ones that I've looked at and have actually used. I'm primarily familiar with SolidWorks. It's industry standard, primarily used for engineering, as there's a lot of simulation tools and things like that that go along with it that allow you to do finite element analysis on certain parts under certain loading conditions. Um, its biggest con, however, is its price. It can be thousands of dollars for a single seat for a company to use. So a lot of the basic blueprints and things like that are done on less expensive programs like um, Rhino or Blender or even SketchUp in some cases. SketchUp is primarily geared towards beginners and architects, especially landscape architectures, as the tools allow for um, simplicity in designing lines and creating complex surfaces. Um, AutoCAD is really big into like 2D CAD software as well as 3D. And the one we used in this course, Inventor, was new to me. I hadn't actually experienced Inventor before. I had used actual AutoCAD in the past, but this was new to me. Each one is typically designed for a specific audience. Like Blender in this case is primarily geared towards animation and art. They would use it to create video game characters or movie characters or something like that. Other programs like Rhino can actually do like double duty. It's good for animation or engineering applications. So next we come into CNC based machines. Now these machines are, it's kind of a wide definition, as CNC stands for computer numerical control. So pretty much any tool, any machining tool that is controlled by a computer can fall under this category. They have many different types of machines, from milling machines, routers, lathes, laser cutters, and plasma cutters. I mean, pretty much you name a tool in a shop, and there's probably a computer-controlled version. Um, they work on different principles. Even 3D printing is a CNC machine. It works differently than most others, as most others, like a CNC router, work on subtractive manufacturing. You start with a large block of material and you slowly shave it away until you've revealed the final part that you want. 3D printing works from the opposite end. You start with nothing and you slowly build layer upon layer, which has some benefits. You can create much more intricate designs than you can with typical manufacturing. Its biggest drawback is its time. It takes a lot of time to 3D print complex objects, especially with high resolution or really thin layer heights. They CNC machines, primarily the subtractive manufacturing ones, work in three basic different principles: 2, 2.5, and 3D operations. Two dimensions are kind of straightforward. They only move in the X and Y, so they create just simple channels at a given depth throughout their process. Now, if you have a tool that starts varying the depth, like can mill a half-inch hole, half-inch deep in one section, and then automatically go to a different one and do an inch and a half, that introduces the 2.5 dimensions of movement. The third dimension, it would be like a CNC router, being able to move vertically, horizontally, all simultaneously to create complex geometries and things like that. So next we come to different careers in 3D building. So careers, I mean, in the modern world of computers, 3D animation, construction, design, analysis is so prevalent in so many different fields. The few listed are just a fraction of what are actually out there. Video game designers, they would use like CAD software and 3D printing to design and bring their creative side to life. They'd give it a physical form with 3D printing. They use it to sell promotional items, for example. Manufacturing and production, I'm currently working as an Amazon robotics technician, and they use CAD software just to lay out their conveyor systems in their warehouses and track packages and things like that. Architecture, obviously, I mean, the CAD software generates plumbing, electrical, where your doors and windows are, framing blueprints. All of this is done on computer to simplify and make changes a lot easier. Animation and film are again really big. They're kind of tied into the video game designer. They use the software to create characters or scenes or structures or objects that would be too expensive, too costly, or just impractical to do in the real world. So next we come into the project that I've been working on this semester. This semester I've been working on, it's called a cable track, or cable chain in some cases. I personally own a 3D printer, and the purpose of this was to decrease the wear and tear on the electrical wires that provide power, sensors, and vision to the print head. The print head moves back and forth rapidly, multiple times throughout a print. So these wires are constantly bending back and forth, back and forth. And so what a cable track will do is it restricts how quickly they bend. And the picture here it was my design of it. The target market was specifically for 3D printers, but it can be applied to any technology-based system that, like a CNC router, the router itself moves back and forth repeatedly. So having one of these cable chains there would help things as well. It improves the lifespan and predictability of your umbilical cables. This was my first introduction to it. I was doing simple research on how I could improve it, and I came across this image, and I thought it was a brilliant idea, and I wanted to pursue it. So this was my starting concept, and I narrowed it down to essentially three basic components. First one is the control board mount. This piece would not move. It would stay stationary, and the wires would come out of it and go into the control board. The next piece is the access mount. This would actually attach to like the print head and would be the piece moving back and forth where the wires would come out of and go into the print head itself. And then finally the actual cable chain segment. This could be printed as many times over and over. They interlock to adjust the length of it. And this is a picture of a simulated assembly of it. It gives you an idea of how it will bend in the limits of it. The project has been largely successful. I did learn I need to increase my tolerances. Right now, like the connecting points are only 0.02 millimeters different, which isn't practical for 3D printing. I mean, a small nozzle size is like 0.2 millimeters, so it's well within the margin of error, so printing this would be impractical. So I would definitely make that change. This simple video kind of showing the individual pieces of it as it comes apart. Finally, the conclusion. This semester has been phenomenal. I've really enjoyed this class. The knowledge I have gained has been incredibly beneficial in my own hobby of 3D printing, and it's also inspired me to go beyond and actually consider pursuing a career in something similar to this, like actual additive manufacturing. That concludes this presentation. Thank you so much for a wonderful semester, and have a good one.